Let us learn about Gd&t basics. What is meant by Gd&t? Gd&t stands for Geometric Dimensioning and Tolerancing. It is a system of symbols, rules and definitions used to define the size, shape, form, orientation and location of features on a part. It is a symbolic language used on engineering drawings and models to define the allowable deviation of feature geometry. Dimension is a geometric characteristic, the size of which is specified such as length, angle, location or center distance, etc. Tolerance on a dimension is the total permissible variation in its size, which is equal to the difference between the limits of size to allow an object to function correctly. Now, there are three types of tolerances: limit dimension type, unilateral type, bilateral type. Limit dimensions are two-dimensional values stacked on top of each other. These show the largest and smallest values allowed. Anything in between these values is acceptable. Unilateral type exists when a target dimension is given along with the tolerance that allows variation to occur in only one direction. A bilateral tolerance exists if variation from a target dimension is shown occurring in both the directions, positive and negative. If no tolerances are specified, then general tolerances are applied at the dimension level, unless otherwise specified. Now let us learn some basic concepts. Datum. A datum is a theoretical exact feature from which dimensional measurement is done, which is generally chosen as an edge or feature which has the greatest influence in a specific measurement. A datum feature is a part feature that contacts a datum. It is denoted with the capital alphabetic letters. These letters are in boxes and tied to the datum feature with the black color filled triangle as shown below. There are three types of datum and all are perpendicular to each other: primary datum, secondary datum and tertiary datum. Its presence shown in the below example of feature of control frame. Primary datum. The primary datum feature has at least 3 points of contact with its datum plane. It controls 3 degrees of freedom of the feature, means 3 degrees of freedom are restricted, that is, rotation around x-axis, rotation around y-axis, movement along the z-axis. Secondary datum. The secondary datum feature has at least 2 points of contact with its datum plane. It controls 2 additional degrees of freedom of the feature, means 2 additional degrees of freedom are restricted, rotation around z-axis, movement along the y-axis. Tertiary datum. The tertiary datum feature has at least 1 point of contact with its datum plane. It controls 1 additional degree of freedom of the feature, means 1 additional degree of freedom are restricted, that is movement along the x-axis. These are the 14 standard characteristics and their symbols of Gd&t. These 14 characteristics fall into 5 different control types. They are form, profile, location, orientation and runout. Let us learn about straightness characteristic. Its control category, form type, and it controls straightness of a feature in relation to its own perfect form. In the given example, tolerance zone of 0.1 of cylindrical feature will be measured using dial gauge by moving its plunger on the surface of the feature in a straight line, and deflection of the dial gives actual straightness value. That value should be within the tolerance zone. Let us discuss about flatness characteristic. Its control category, form type, and it controls the flatness of a surface in relation to its own perfect form. In the given example, tolerance zone of 0.1 of the rectangular feature will be measured using dial gauge by moving its lever plunger on the surface of the feature, which is located on the 2 identical B blocks as shown in the picture, and deflection of the dial gives actual flatness value. That value should be within the tolerance zone. Let us learn about circularity characteristic. Its control category, form type, and controls the form of a revolved surface in relation to its own perfect form by independent cross sections. In the given example, tolerance zone of 0.1 of the cylindrical feature will be measured using dial gauge by moving its plunger on the surface of the feature in a circular direction, which is located on the 2 identical V blocks as shown in the picture. And deflection of the dial gives actual circularity value. That value should be within the tolerance zone. Let us go through cylindricity characteristic. Its control category form type and controls the form of a revolved surface like circularity but applies simultaneously to entire surface. In the given example, tolerance zone of 0.005 of the cylindrical feature will be measured using dial gauge by moving its plunger on the entire surface of the feature in a circular direction, which is located on the two identical V blocks as shown in the picture. And the deflection of the dial gives actual cylindricity value. That value should be within the tolerance zone. Selection of points on the cylindrical surface based on tightness of the tolerance. Let us go through profile of a line characteristic. Its control category profile type and controls the profile of a line at any point of the feature, usually of a curved shape. In the given example, tolerance zone of 0.25 of the curved feature will be measured using dial gauge by moving its plunger on the surface of the feature by keeping master profile as a reference for the movement, as shown in the picture. And deflection of the dial gives actual profile of the line value. That value should be within the tolerance zone. Let us study profile of a surface characteristic. Its control category profile type and controls the profile of a surface by describing a three-dimensional tolerance zone around a surface, usually which is an advanced curve or shape. In the given example, tolerance zone of 0.25 of the curved feature will be measured using CMM by moving its probe on the surface of the feature by taking necessary reference points as shown in the picture and automatically calculates actual profile of the surface value. That value should be within the tolerance zone. Here, CMM is a coordinate measuring machine used for measuring the physical geometrical characteristics of an object. Its probe will measure the defined characteristics by taking necessary reference points. Probes may be mechanical, optical, laser or white light, etc. This machine takes readings in 6 degrees of freedom and displays those on the computer monitor. Let us study about parallelism characteristic. Its control category orientation type and controls orientation of a feature which is nominally parallel to the primary datum of its datum reference frame. In the given example, tolerance zone of 0.1 of the rectangular feature will be measured with respect to datum A using dial gauge by moving its lever plunger on the surface of the feature which is placed on the another respective surface as shown in the picture. And deflection of the dial gives actual parallelism value with respect to datum A. That value should be within the tolerance zone. Let us learn about perpendicularity characteristic. Its control category orientation type and controls orientation of a feature which is nominally perpendicular to primary datum of its datum reference frame. In the given example, tolerance zone of 0.1 of the feature will be measured with respect to datum A, which is clamped on the U-clamp V block using dial gauge by moving its plunger in perpendicular direction of the surface of the feature as shown in the picture. And deflection of the dial gives actual perpendicularity value with respect to datum A. That value should be within the tolerance zone. Let us discuss about angularity characteristic. Its control category orientation type and controls orientation of a feature at a specific angle in relation to its primary datum of its datum reference frame. In the given example, tolerance zone of 0.25 of the feature will be measured with respect to datum A by using dial gauge by moving its plunger in a straight line which is located on the sine bar and slip gauge setup as shown in the picture. And deflection of the dial gives actual angularity value with respect to datum A. That value should be within the tolerance zone. Let us study about concentricity characteristic. Its control category, location type and controls the central axis of referenced feature to a datum axis. It is also called as coaxially. In the given example, tolerance zone of 0.1 of the cylindrical feature will be measured with respect to datum A using dial gauge by moving its plunger on the surface of the feature in a circular direction by rotating reference or respective portion of the feature which is located on the B block as shown in the picture. And deflection of the dial gives actual concentricity value with respect to A. That value should be within the tolerance zone. Let us go through symmetry characteristic, its control category, location type, and controls uniformity of two features on a part across a datum plane. In the given example, tolerance zone of 0.05 of the feature will be measured with respect to datum A using dial gauge by moving its lever plunger on the surface of the feature which is first placed on one surface, then another, as shown in the picture. And deflection of the dial gives actual symmetry value with respect to A. That value should be within the tolerance zone. Let us learn about position characteristic, its control category, location type, and controls variation of a feature from a specified exact true location. In the given example, tolerance zone of 0.1 at maximum material condition of the feature will be measured with respect to datums A, B and C using CMM probe by taking reference points of the feature as shown in the picture, and automatically calculates actual position value with respect to datums A, B and C. That value should be within the tolerance zone. Let us study circular runout characteristic, its control category, runout type, and control circularity and coaxiality of each circular segment of a surface independently about a coaxial datum. In the given example, tolerance zone of 0.1 of the feature will be measured using dial gauge by moving its plunger on any point of the feature with respect to datum A, which will be rotated by placing it on the B block as shown in the picture. And deflection of the dial gives an actual circular runout value. That value should be within the tolerance zone. Let us learn about total runout characteristic, its control category, runout type, and control circularity, straightness, coaxiality and taper of a cylindrical surface about a coaxial datum. In the given example, tolerance zone of 0.05 of the feature will be measured using dial gauge by moving its plunger on the entire surface of the feature with respect to datum A, which will be rotated by placing it on the B block as shown in the picture. And deflection of the dial gives an actual total runout value. That value should be within the tolerance zone. Maximum material condition, MMC. MMC describes the condition of a feature where maximum amount of material exists within its dimensional tolerance. This condition exists at minimum clearance or maximum interference. Example, largest pin diameter, smallest hole size. In the picture you can see that shaft with diameter 10 mm with tolerance plus or minus 0.1, MMC is equal to 10.1, and for the hole diameter 10 mm plus or minus 0.1 tolerance, MMC is equal to 9.9 mm. Least material condition, LMC. LMC describes the condition of a feature where the least amount of material exists within its dimensional tolerance. This condition exists at maximum clearance or minimum interference. Example, smallest pin diameter, largest hole diameter. In the following example, we can see that shaft with the diameter 10 mm plus or minus 0.1 tolerance, LMC is equal to 9.9 mm. And for the hole diameter 10 mm plus or minus 0.1 tolerance, LMC is equal to 10.1 mm. Bonus tolerance. Bonus tolerance is an additional tolerance for a geometric control. It is the additional tolerance available for a geometric control attached to a feature of size with MMC, maximum material condition, and LMC, least material condition modifier. So bonus tolerance is equal to shaft size at MMC minus shaft size at LMC. Example, shaft of diameter 25 plus or minus 3. Here at MMC, shaft size is equal to diameter 28, so bonus tolerance is 0. For shaft size diameter 27, bonus tolerance is 1. For shaft size diameter 26, bonus tolerance is 2, and so on. So total bonus tolerance is equal to MMC minus LMC, that is diameter 28 minus diameter 22, that is equal to 6. Let us discuss about virtual condition. Virtual condition is the theoretical extreme boundary condition of a feature of size generated by the collective effects of MMC, size limit of a feature, and any applicable geometric tolerances. In the below figure of hole of diameter 10 plus or minus 0.2, the MMC is equal to 9.8. The worst case would be the smallest hole that is also out of position, that is 9.8 minus 0.3, that is equal to 9.5. This case is called virtual condition. Resultant condition. This is similar to virtual condition but considers least material condition of the feature, that is least material condition plus stated geometrical tolerance plus bonus, that is equal to 10.2 plus 0.3 plus 0.4, that is equal to 10.9. This represents area where any portion of the hole's edge may possibly fall. Allowance. Allowance is defined as the difference between the maximum material limits of the mating parts. Allowance is the minimum clearance or maximum interference between mating parts, that is equal to MMC hole minus MMC shaft. Clearance. Clearance is the loosest fit or maximum intended difference between mating parts, that is equal to LMC hole minus LMC shaft. Let us discuss about different types of fits. Clearance fit. The tolerance of the parts is such that the largest shaft is smaller than the smallest hole. In this, one part fits easily into another with the resulting clearance gap. In this picture we can see that tolerance on the shaft is equal to 0.002 and tolerance on the hole is equal to 0.002. Minimum clearance 0.660 minus 0.655, that is equal to 0.005, and maximum clearance 0.662 minus 0.653, that is equal to 0.009. Interference fit. In this type, one part must be forcibly fitted into another, that is, maximum clearance is always negative. In this example, we can see that tolerance on shaft is equal to 0.001 and tolerance on the hole is equal to 0.001. Minimum clearance is equal to 0.510 minus 0.513, that is equal to minus 0.003 inch. That is, the tightest fit 0.003 in interference. Maximum clearance, that is equal to 0.511 minus 0.512, that is equal to minus 0.001 inch. The loosest fit 0.001 in interference. Transition fit. The tolerance of the parts is such that the allowance is negative and the maximum clearance is positive. A transition fit exists when the maximum clearance is positive and minimum clearance is negative. In this example, tolerance on the shaft is 0.005 and tolerance on the hole is 0.005. Minimum clearance, that is equal to 0.510 minus 0.517, that is equal to minus 0.007 inch. The tightest fit is 0.007 in interference. Maximum clearance, that is equal to 0.515 minus 0.512, that is equal to 0.003 inch. The loosest fit is 0.003 in clearance. Let us learn about projected tolerance zone. The projected tolerance is a modifier used for threaded or press fit holes in order to ensure the proper fitments of the mating parts by means of studs, pins, screws, bolts, etc. The projected tolerance zone extends above the surface of the part to the functional length of the pin, stud or screw relative to its assembly with the mating part. It controls the perpendicularity of the hole to the extent of the projection from the hole as it relates to the mating part clearance. In the following example, let us take plate with the hole in which a stud will be inserted with the positional tolerance with respect to datum A. Here you can see that positional tolerance of dia 0.2 applied to the datum A of lower plate that can be varied at the worst case within the mentioned zone as shown in the figure. Now it is clear that if the stud axis follows the worst case, then the stud may interfere with the mating plate. For avoiding that interference, specifying the projected tolerance zone in the drawing is required. So here you can see that projected tolerance of pi has been mentioned in the drawing after the value of positional tolerance. The meaning of the projected tolerance of pi is the positional tolerance zone of point 2 will extend by pi units beyond the surface of the bottom plate, and by doing so interference problem will avoid. Tangent plane. Tangent plane is a simulated flat plane that contacts the high points of a surface for orientation of the datum. This modifier indicates that only the tangent plane of the tolerance surface needs to be within this tolerance zone. In the example, you can see that tangent plane selected within the zone of point 3 with respect to datum B for calculation purpose of parallelism. Regardless of feature size, RFS. RFS is a default modifier if no modifier symbol shown in the feature control, which is used when the size feature does not affect the specified tolerance. It is used and implied when the geometrical tolerance is to remain the same no matter what size hole or shaft is produced within its tolerance limit. In this given example, bonus tolerance 0.4 not applicable. Therefore, the position of the shaft must lie in between tolerance zone of 0.3 regardless of feature size. Free state variations. Free state variation is a term used to describe deformation of the part after removal of forces applied during manufacture. Basic dimension. It is used to describe the exact size, profile, orientation or location of the feature. It does not involve any tolerance limits. Reference dimension. It is a dimension usually without tolerance, used for reference purposes only. It does not control production or inspection operations. All around symbol. This indicates that tolerance applies to surfaces all around the part. Dimension origin. A circle used in place of one of the arrowheads on a dimension line indicates the origin for measurement. Conical taper. It is used to indicate taper for conical tapers. This symbol is always shown with vertical leg to the left. Slope. It is used to indicate slope for flat tapers. Datum target. It is a specified point, line or area on the part that is used to establish the datum reference plane for manufacturing and inspection operations. Counterbore. This symbol is used to indicate a counterbore or a spot face. The symbol precedes the dimension of the counterbore with no space. Countersink. This symbol is used to indicate a countersink. The symbol precedes the dimension of the countersink with no space. Square. This symbol is used to indicate that a single dimension applies to square shape. This symbol precedes the dimension with no space between. Depth or deep. It is used to indicate that dimension applies to the depth of the feature. This symbol precedes the depth value with no space in between. Number of places. The X symbol is used along with the value to indicate the number of times a dimension or feature is repeated on the drawing. Statistical tolerance. It is the assigning of tolerances to the related components of an assembly on the basis of statistics. By applying statistical tolerance, tolerances of individual components may be increased or clearances between mating parts may be reduced. Between. This is used to indicate that a profile tolerance applies to several contiguous features or letters may designate where the profile tolerance begins and ends. These letters are referenced using the between symbol. Target point. This indicates where datum target point is dimensionally located on the direct view of the surface. Arc length. This indicates that a dimension is an arc length measured on curved outline. The symbol is placed above the dimension. Continuous feature. It is used to identify a group of two or more features of size where there is a requirement that they may be treated geometrically as a single feature of size. Now let us discuss about surface finish. Surface finish is the allowable deviation from a perfectly flat surface made by some manufacturing process. Surface roughness is a property of the material surface texture which is recognized by an uneven topography as compared to the perfectly flat surface. All machining processes will generate some roughness on the surface. Since all the surfaces may not have functional requirements, so no need to have equal finish everywhere. Roughness can be measured by manual comparison against surface roughness comparator or profilometer or optical method. Surface finish is broken up into three components such as roughness, waviness and form. Here roughness is the machined marks made on the surface by the cutting tool. Waviness is the result of vibration of the tool, and form surface irregularities caused by worn off machine bed or table, etc. So roughness is the measure of finest irregularities of a surface. Waviness is the measure of surface irregularities with the spacing greater than that of surface roughness. Lay refers to the predominant direction of the surface texture. From this figure you can see that for a given sample length, RA is the average variation from mean line. RT is the distance from the highest peak to the deepest valley. RP is the highest peak above the mean line. RV is the deepest valley below the mean line. RZ the average RT over given length. Example, RZ is equal to RT1 plus RT2 plus RT3 divided by 3. These are the symbolic representations of surface roughness. Here, in the first symbol, A obtained by any production process. In the second symbol, A obtained by removal of material by machining. In the third symbol, roughness A obtained without removal of any material. In the fourth symbol, A1 represents upper and A2 represents lower limit of surface roughness value. In the fifth symbol, G represents production method, and in sixth symbol, B represents other than RA value. This is the general RA value in micrometer and its grade number.